Let's just look at the photoelectric PhET. So if you click on this, it'll take you there. This will open up the, it's not working. Well, let's try again. It's running, this is like a little runtime environment for applets, right? I'm going to turn on the light here and you can see there's no voltage being applied. And so if I turn the light on, you can see that, and this is sodium metal. So sodium is a very low work function, right? I think maybe calcium is the next one, right? Platinum would be the highest work function, right? I think, I don't know. But anyway, so sodium, we've got this thing that's very easy to eject electrons, and this light is 400 nanometers, so it's pretty energetic light. And one of the things you can do is you can change the, and if you make it shorter wavelength, right, they're going faster. And if you make it longer wavelengths, they're going slower. And then at some point, none of them come off, right? It's like, okay, where is that? 546. There we go, 532. So somewhere between 546 and 532 nanometers, there's a wavelength that doesn't have sufficient energy to even eject the electrons off the sodium metal, right? And so that's one of the calculations that I have you do in the lab, is to figure out, what that work function is, and you can do it by changing this wavelength, right? That's not how they did it, because of course they only had certain wavelengths to work with. They did it by extrapolating, right? But anyway, the other thing you can do now is we can turn this on and give it a forward potential. And now you can see the electrons, once they're ejected, they accelerate, right? And this is what photocells do, right? It's like no light, no current. If you have a light, there is a current, right? So that's what photocells were used for, right? And then what I do is I have them mess around with potential here and figure out with it at 350 nanometers, for example. Let's see if I can get it there. At 350 nanometers, the question is, what if we reverse the potential? And this is, of course, the experiment, right? There's going to be some potential that slows them down, right? So let's try -1. -1 isn't enough, right? Let's go -1.2. So I'm just typing in the text box. You can do that up here too. You can type in a number like 352, enter, right? So at 350, and you have to hit enter. The kids don't understand that, right? So at 350, and then let's try this, another one of these guys here. How about -1.4? Is that enough? Yeah, see, so no, 1.4 is they don't even make it there, right? So we have to try -1.3. We're going to find a voltage, right, that stops all the electrons, and that'll be the stopping potential. So I do that a few times in the lab. Okay, so 1.2, let's see, so 1.25. Does that do it? No. Getting closer. How about -1.22? This is for sodium metal, right? Okay, now notice it'll touch that plate, but it's got to go into the plate. It has to disappear. So that is really close. I don't know if, let's try a 1.21. Yeah, there we go. I think that is the stopping potential for this, right? Okay, and that's a factor of the work function of this and the energy of those photons. Okay, but anyway, it just lets them see, if you have a forward acceleration, if you have a backward acceleration, you can calculate work functions, you can calculate the stopping potential. Anyway.